The blizzard hit the Montana Territory on January 7, 1881, with a ferocity that old-timers said they'd never seen before. Wind screamed through the mountains at 60 miles per hour, driving snow horizontally with such force that it penetrated every crack and gap in every structure. The temperature dropped to 39 degrees below zero and stayed there for 3 days. In the scattered cabins throughout the Bitterroot Valley, the battle for survival became desperate. Men burned every stick of wood they could find, fed fires constantly, and still watched helplessly as temperatures inside their cabins dropped to single digits above zero. Frostbite was common. Hypothermia was a real threat. At least 2 trappers froze to death in their cabins when their fires went out and they couldn't restart them in the wind. But 3 miles up a narrow canyon, in a cabin that everyone said had a broken chimney that would never work properly, a Norwegian trapper named Lars Henriksen sat comfortably in his wool shirt, reading by lamplight, while his thermometer showed 8 degrees above zero. 8 degrees above zero. That's 47 degrees warmer than outside. 47 degrees warmer with a fire that had been burning steadily, but not intensely for 18 hours. While his neighbors frantically fed roaring fires that barely kept their cabins above freezing, Lars maintained comfortable warmth with what looked like a dangerously inadequate fire in a chimney that everyone swore was built wrong and would kill him with smoke. When the blizzard finally broke on January 10th and travel became possible again, a trapper named Samuel Grant made his way to Lars's cabin expecting to find a frozen corpse. What he found instead was Lars alive, warm, and preparing breakfast on a stove that seemed to be barely burning. Sam stood in the doorway, snow still clinging to his beard, staring at the scene in disbelief. "Your chimney," Sam said, his voice rough from 3 days of breathing smoke in his own poorly functioning cabin. "Everyone said it was built wrong. Everyone said the blocks you put in it would make smoke back up and kill you. But you're warm, warmer than anyone else in the valley. How is that possible?" Lars gestured toward the stove and the strange chimney rising from it. "The chimney is not broken. It is designed exactly as I intended. What looks wrong to you is what makes it work. Those blocks everyone warned me about, they are not mistakes. They are the key to everything." Sam moved closer to the stove, examining the chimney. It looked wrong, completely, obviously wrong. Every few feet, the chimney had visible obstructions, what looked like bricks or stones positioned to partially block the flow of smoke. These obstructions created what seemed like dangerous restrictions that should have caused smoke to back up into the cabin, but the cabin air was clear. No smoke, no fumes, just warm, clean air. "I don't understand," Sam said. "These blocks, they should stop the smoke from rising. They should make your cabin fill with smoke." "How are you not dead?" Lars smiled. "Because the blocks do not stop the smoke. They slow it down. They make it give up its heat before it escapes. Every other chimney in this valley throws heat away as fast as the fire can make it. My chimney captures that heat and keeps it where it belongs, in my cabin. That is why I'm warm, and that is why everyone else is freezing." What Lars Henriksen had built was a chimney that violated every principle of conventional chimney construction. It had deliberate obstructions that created turbulence and forced smoke to change direction multiple times before exiting. It had thermal mass positioned to absorb heat from the smoke. It had features that trapped heat without trapping smoke. To anyone trained in conventional building, it looked catastrophically wrong. A chimney built by someone who didn't understand how chimneys worked. But Lars understood exactly how chimneys worked. And more importantly, he understood how conventional chimneys wasted heat and how that waste could be eliminated. His broken chimney trick, the design everyone mocked and predicted would fail, had just kept him alive and comfortable through the worst blizzard Montana Territory had seen in decades. And the story of how he built it, why it worked, and why everyone was so convinced it was deadly dangerous, reveals deep truths about heat, draft, and the difference between conventional wisdom and actual wisdom. Lars Henriksen was born in northern Norway in 1842, in a region where winter temperatures routinely dropped to 40 below and stayed there for months. Survival in such conditions required sophisticated understanding of heating and insulation. Norwegian builders had developed techniques over centuries for extracting maximum heat from minimal fuel. Lars grew up learning these techniques from his father and grandfather, both of whom were builders. By age 20, Lars understood more about efficient heating than most American frontier builders would learn in a lifetime. When he emigrated to America in 1868 at age 26, he brought this knowledge with him. He worked various jobs, logging camps, construction crews, eventually making his way west with the fur trade. By 1878, he'd saved enough to establish his own trap line in the Bitterroot Valley of Montana Territory. The valley was beautiful but brutal. Winter temperatures regularly reached 30 below zero. Firewood required significant effort to harvest. Lars knew that surviving comfortably would require building better than the standard frontier cabin with its standard inefficient fireplace or stove. He selected his site carefully in the summer of 1878. Good southern exposure for passive solar gain, protection from north wind by a ridge behind the cabin, adequate timber and water. He began construction immediately, and from the start, his methods puzzled the few neighbors who saw his work. The cabin itself was built with thick walls, using double log construction with moss insulation between layers. This made sense to people familiar with cold climate building. But the chimney was where Lars's design became controversial. He started by building a standard firebox and hearth using fire brick. Nothing unusual there. But above the firebox, instead of building a straight vertical flue that would carry smoke directly outside, Lars began constructing something far more complex. The chimney rose vertically for 4 feet, then encountered the first baffle. A baffle was a partial obstruction, a brick positioned to force smoke to change direction. Lars's first baffle was a brick extending halfway across the flue opening, positioned on the left side. Smoke rising from the fire would hit this baffle and be forced to move right and then up to get past it. 4 feet higher, a second baffle, this one extending from the right side, forcing smoke to move left and up. 4 feet higher still, a third baffle from the left. The pattern continued. 6 baffles total, alternating sides, each one forcing the smoke to zigzag up the chimney rather than rising straight. This zigging and zagging increased the path length smoke had to travel. It increased contact time between hot smoke and the chimney walls. It created turbulence that mixed the smoke and prevented it from streaming through in a laminar flow. All of this increased heat transfer from the smoke to the chimney structure. But to anyone unfamiliar with the concept, it looked insane. Why would you deliberately obstruct your chimney? Why force smoke to take a longer, more complicated path? Wouldn't that cause smoke to back up into the cabin? A trapper named John Matthews, who had a cabin 5 miles down valley, came to visit during construction. He watched Lars carefully position a baffle brick, mortar it in place, and step back to examine his work. "Lars," Matthews said slowly, "I think you've made a mistake. That brick is blocking your chimney. Smoke needs to rise straight up. If you put obstacles in the way, the smoke will have nowhere to go except back into your cabin." Lars continued working, adjusting the mortar. The smoke will rise. But it will rise slowly, giving up heat as it goes. Fast smoke wastes heat. Slow smoke shares heat. Matthews shook his head. "I've built 3 cabins and 4 chimneys. Never once did I put anything in the flue to slow down the smoke. You keep the path clear so smoke escapes quickly. That's how chimneys work. That is how most chimneys work." "Yes," Lars agreed, "and that is why most chimneys waste most of the fire's heat." "My chimney will waste almost nothing." Matthews left, convinced Lars was making a terrible mistake. He told other trappers about the crazy Norwegian building a chimney with obstructions in it. The story spread. People shook their heads. Some predicted Lars would die of smoke inhalation within a month of lighting his first fire. Others thought he'd realize his mistake, tear down the chimney, and rebuild it properly. Lars ignored the predictions and continued building. The baffles were only the first part of his design. The chimney itself was built with double walls. The inner wall was fire brick, resistant to the heat and corrosive effects of smoke. The outer wall was regular brick. Between the inner and outer walls, Lars left a 1-inch gap. This gap was filled with sand. The sand layer served multiple purposes. It acted as insulation, keeping the inner wall hot so smoke wouldn't cool too quickly. It acted as thermal mass, storing heat absorbed from the smoke, and it prevented heat from radiating through the outer wall and being wasted to the outside air. The outer wall of the chimney extended beyond the inner wall at several points, creating shelves or caps inside the chimney. These caps provided additional surface area for heat transfer. Hot smoke would rise, hit a cap, spread out across its surface, transfer heat, and then find the opening to continue upward. More surface contact meant more heat extraction. Lars calculated, using methods his grandfather had taught him, that smoke entering his chimney at 1,000 degrees Fahrenheit would exit at approximately 400 degrees. 600 degrees of heat extracted from smoke that would otherwise have been wasted up the chimney. That 600 degrees would heat the massive brick chimney structure. The chimney, weighing approximately 3 tons, would become a thermal battery, storing heat and radiating it into the cabin long after the fire died down. The final element of Lars's design was the damper system. At the very top of the chimney, just before the smoke exited, Lars installed a heavy steel plate that could be rotated to partially close the flue opening. This damper allowed him to control the draft. Wide open, the damper provided maximum draft for starting fires and burning very hot. Partially closed, it restricted airflow, slowing combustion and forcing smoke to spend more time in the chimney, transferring more heat. Completely closed, it sealed the system when no fire was burning, preventing warm air from escaping up the chimney. This damper was controversial because conventional wisdom said you should never restrict chimney draft. Reduced draft meant reduced airflow, which meant incomplete combustion, which meant dangerous carbon monoxide production and creosote buildup. But Lars knew that this conventional wisdom applied to chimneys that relied on high draft to function. His chimney was designed to operate with moderate draft. The baffles, the thermal mass, and the controlled airflow created a different combustion dynamic. When Lars fired up his stove for the first time in November of 1878, several neighbors came to watch, some hoping to learn, others expecting disaster. Lars loaded well-seasoned pine into the firebox, adjusted the air intakes on his stove. To provide adequate oxygen, opened the damper fully to establish strong initial draft, and lit the fire. The fire caught immediately and burned hot. Smoke rose into the chimney, hit the first baffle, swirled, changed direction, continued upward, hit the second baffle, swirled again, continued the zigzag pattern through all 6 baffles, and exited through the top of the chimney. No smoke backed up into the cabin. The air remained clear. Within 30 minutes, the chimney began radiating heat. You could feel warmth coming from the brick structure even though the fire had been burning less than an hour. This was the thermal mass absorbing and re-radiating heat. Lars adjusted the damper to half-closed position, reducing draft and slowing combustion. The fire continued burning steadily but not intensely. Smoke continued rising and exiting. The cabin temperature climbed steadily. By evening, 6 hours after lighting the fire, the cabin was 65 degrees inside while outside temperature was 20 degrees, a 45-degree differential. Lars's fire was moderate, consuming perhaps 1/4 the wood per hour that his neighbors' stoves consumed, but his cabin was warmer. The heat that would normally have escaped up the chimney was being captured by the baffles and thermal mass, stored in 3 tons of brick, and radiated into the cabin. John Matthews, who'd warned Lars about the block chimney, stood inside the warm cabin, feeling heat radiate from the chimney structure, and slowly acknowledged that maybe, just maybe, Lars knew something he didn't. Over the next month, Lars refined his operation of the system. He learned the optimal damper settings for different conditions. He learned how to build fires that burned hot initially to establish good draft, then moderated for long, efficient burns. He learned that the thermal mass of the chimney meant he could let fires burn down to coals overnight, and the stored heat in the brick would keep the cabin comfortable until morning. His wood consumption was approximately 1/3 of what neighbors used. His cabin was consistently 5 to 10 degrees warmer than neighboring cabins, and he was developing a reputation as either a genius or a very lucky fool, depending on who you asked. Then came January 1881, and the blizzard that would prove everything. The storm hit with almost no warning. Temperature dropped from 20 degrees to 39 below in less than 6 hours. Wind reached sustained speeds of 50 to 60 miles per hour, with gusts even higher. Snow fell so heavily that visibility was measured in feet. Every cabin became a siege against the cold. In conventional cabins with conventional chimneys, the battle was desperate. Men stoked fires constantly, burning wood as fast as they could feed it. But conventional chimneys don't work well in extreme wind. The wind created downdrafts, forcing smoke back into cabins. It also created such strong negative pressure that fires burned out of control, consuming fuel rapidly while sending most of the heat straight up the chimney. Cabin temperatures dropped despite maximum fire output. Some men gave up trying to heat the whole cabin and instead built small fires in corners, huddling close for warmth, letting the rest of the structure freeze. Others burned furniture, floorboards, anything combustible when firewood ran out. The situation was life-threatening. In Lars's cabin, conditions were different. The first challenge was the wind effect on his chimney. The violent wind created extreme turbulence at the chimney top. This could have caused downdrafts or draft reversal, forcing smoke back down. But Lars's chimney design was inherently resistant to wind effects. The baffles that slowed smoke also dampened pressure fluctuations. Sudden gusts at the chimney top didn't immediately translate to draft changes in the firebox because the smoke had to navigate 6 direction changes and multiple restrictions. This created a buffering effect. The chimney continued drafting properly even in 60-mile-per-hour wind. Lars monitored carefully during the first hours of the storm. He adjusted his damper slightly more open to account for the enhanced draft from wind. He maintained a steady, moderate fire, not pushing for maximum heat, but rather for optimal efficiency. The 3-ton thermal mass of his chimney was already warm from days of use. It would continue radiating heat even if conditions prevented optimal fire operation. By the second day of the storm, when temperatures outside hit 39 below, Lars's cabin was 8 degrees above zero. 8 degrees. That's 47 degrees warmer than outside. His fire was steady but not large. Wood consumption was modest. The cabin air was clear and breathable. No smoke, no fumes, no carbon monoxide. The chimney system was working exactly as designed. Lars took temperature measurements every few hours, recording them in a journal. Outside, 39 below. Cabin interior, 8 above. Fire consumption rate, approximately 2 pounds of wood per hour. Cabin heat output, estimated at 12,000 BTUs per hour. For comparison, neighbors' cabins were burning 6 to 8 pounds of wood per hour, producing nominal output of 30 to 40,000 BTUs per hour, but achieving interior temperatures of 0 to 5 degrees. Their efficiency, calculated as useful heat divided by fuel energy, was approximately 15 to 20%. Lars's efficiency was approximately 65%. 3 times better. This efficiency difference was the margin between comfort and crisis. When Samuel Grant finally made it to Lars's cabin after the storm broke, he found Lars not just alive but comfortable. Sam stood in the warm cabin, shaking his head in disbelief. He placed his hand on the chimney. It was warm to the touch, radiating steady heat. The fire in the stove was moderate, nothing special. Yet the cabin was warmer than Sam's cabin had been at any point during the storm, despite Sam burning every piece of wood he owned and nearly burning his cabin structure itself. "This shouldn't work," Sam said. "By every rule I know, this chimney should have failed. The blocks should have caused smoke backup. The wind should have created downdrafts. The restricted draft should have produced carbon monoxide. But you're alive, and you're warmer than anyone else in the valley." "How?" Lars explained the system patiently. The baffles that looked like mistakes were actually heat extractors. They forced smoke to give up heat to the chimney mass. The thermal mass stored that heat and released it slowly, creating stable temperatures rather than the boom and bust cycle of conventional stoves. The restricted draft, carefully controlled with the damper, ensured complete combustion at lower rates, maximizing efficiency. The double-wall construction and sand insulation kept the inner flue hot enough to prevent creosote condensation while capturing heat for the cabin. Every element that looked wrong was actually precisely right for extracting maximum heat from minimum fuel. Sam listened, tried to understand, and finally asked the question that mattered most. "Could you build one of these for me?" Lars agreed. That spring and summer of 1881, Lars built 5 chimneys using his baffle design for neighbors who'd survived the blizzard and wanted better heating for the next winter. Each installation was customized to the specific cabin and stove. Some used 4 baffles instead of 6. Others used different baffle spacing. But the core principle remained: use partial obstructions to force smoke to transfer heat to thermal mass before escaping. Results were universally positive. The following winter, 1881 to 1882, was milder than the previous year but still severe. Cabins with Lars-style chimneys used 40 to 60% less wood than conventional cabins while maintaining higher interior temperatures. The efficiency advantage was undeniable. If this story about forgotten heating innovations is teaching you things you've never heard before, things that could still be useful today, please take a moment to subscribe to this channel. Hit that subscribe button and turn on notifications. We dig deep into historical techniques that solved real problems with elegant engineering. Your subscription helps us continue bringing you these stories. Now let's explore the science behind why Lars's broken chimney trick worked so spectacularly well. The physics of Lars's chimney operates on several interconnected principles that modern engineers would recognize as heat exchanger design, thermal storage, and draft management. First, the heat exchanger function. A conventional straight chimney allows hot exhaust gases to rise rapidly from the fire to the exterior. The gases might spend 2 to 3 seconds in contact with the chimney walls. This brief contact time limits heat transfer. Only a small fraction of the heat in the smoke transfers to the chimney structure. Most exits to the atmosphere wasted. Lars's baffles increased contact time dramatically. Smoke entering the chimney had to navigate 6 direction changes, each one forcing it to slow down, spread out, and contact more surface area. The effective path length was approximately 50% longer than a straight chimney of the same height. The contact time increased from 2 to 3 seconds to 5 to 7 seconds. More time meant more heat transfer. The turbulence created by the baffles also enhanced heat transfer. In straight chimneys, smoke rises in relatively smooth, laminar flow. The center of the smoke column might be much hotter than the edges because mixing is limited. The baffles disrupted laminar flow and created turbulent mixing. This brought hot gases into contact with chimney walls more effectively, improving heat transfer rates. The result was that smoke exiting Lars's chimney at 400 degrees had given up 600 degrees to the chimney structure, compared to conventional chimneys where smoke might exit at 700 degrees, giving up only 300 degrees. Second, thermal mass storage. Lars's chimney contained approximately 3 tons of brick. Brick has a specific heat capacity of about 840 joules per kilogram per degree Celsius. 3 tons equals approximately 3,000 kilograms. Heating this mass from ambient room temperature, say 60 degrees, to an average temperature of 200 degrees, a 140-degree increase, required approximately 353 million joules. That's roughly 98 kilowatt-hours of stored energy. This stored energy was released slowly over many hours. If the thermal mass released heat at a rate of 2,000 watts, 2 kilowatts, continuously, the stored energy would last approximately 49 hours before the mass cooled back to room temperature. In practice, Lars would refire before the mass cooled completely, maintaining it in a charged state. The thermal mass created thermal inertia. The cabin temperature couldn't drop rapidly because the mass was continuously releasing stored heat. Even if the fire went out completely, the cabin would cool slowly, over many hours, giving plenty of time to restart the fire. This thermal buffer was crucial during the blizzard, when tending fires was difficult and dangerous. Third, draft management and combustion control. Draft is the pressure difference that pulls air through a fire and exhaust up a chimney. Strong draft creates fast, hot fires that consume fuel rapidly. Weak draft creates slow, potentially incomplete combustion. Lars' adjustable damper allowed him to control draft precisely, optimizing for efficiency rather than maximum output. By partially closing the damper, Lars reduced airflow through the fire. This slowed combustion rate, making each load of wood last longer. But crucially, the reduced airflow didn't cause incomplete combustion because Lars's stove was designed with proper air intakes positioned to ensure adequate oxygen reached the fire. The combustion was slower but still complete, producing carbon dioxide and water vapor rather than carbon monoxide. Modern EPA-certified wood stoves use similar approaches, controlling air supply to achieve long, clean burns. Fourth, prevention of heat loss through the chimney when no fire burns. In conventional chimneys, warm cabin air rises and escapes through the chimney continuously, even when no fire is burning. This convective heat loss can be significant. Lars's damper, when closed, eliminated this loss pathway. The warm air in the cabin stayed in the cabin. This seems simple but makes a meaningful difference in heat retention. Fifth, resistance to wind effects. Wind blowing across a chimney top can create downdrafts or draft reversals, especially gusty wind. Lars's baffled chimney was resistant to these effects because the baffles damped pressure fluctuations. A sudden wind gust might create momentary pressure change at the chimney top, but that pressure change had to propagate through a complex path with multiple direction changes. By the time it reached the firebox, the pressure fluctuation was greatly reduced. This gave Lars's system stability in high wind that conventional chimneys lacked. The mathematical analysis of heat extraction is straightforward. Exhaust gases from wood combustion have a mass flow rate dependent on burn rate. At Lars's typical burn rate of 2 pounds of wood per hour, approximately 4 kilograms per hour, the exhaust mass flow was roughly 20 kilograms per hour. The exhaust gases have a specific heat capacity of approximately 1 kilojoule per kilogram per degree Celsius. Cooling the exhaust by 600 degrees, from 1,000 to 400, extracted approximately 12,000 kilojoules per hour. That's approximately 3.3 kilowatts continuously. This 3.3 kilowatts of heat, captured from smoke that would otherwise have been wasted, was sufficient to maintain an 8-degree interior temperature when outside was 39 below. A 47-degree temperature differential requires overcoming heat losses through walls, roof, floor, and infiltration. Lars's cabin, well insulated with double walls, probably had a total heat loss rate of approximately 4 kilowatts at 47-degree differential. His fire produced approximately 2 kilowatts directly through the stove. His chimney captured 3.3 kilowatts from the exhaust. Total useful heat was approximately 5.3 kilowatts, exceeding the 4 kilowatt loss rate, which explained the stable 8-degree interior temperature. The creosote question is critical for safety. Creosote forms when smoke cools below approximately 250 degrees Fahrenheit. It's a tarry, flammable substance that accumulates in chimneys and can cause dangerous chimney fires. Lars's design had to prevent creosote formation despite extracting so much heat from the exhaust. The key was the double wall construction with sand insulation. The inner flue wall stayed hot because it was insulated from the outer wall by the sand layer. Even though the outer wall might be 200 degrees, the inner wall where smoke contacted stayed above 300 degrees. Smoke cooled from 1,000 to 400, but the flue surface it contacted never dropped below creosote condensation temperature. Additionally, Lars burned well-seasoned wood and maintained hot, complete combustion. This produced less creosote-forming compounds in the first place, and he cleaned his chimney twice per year, removing any minor creosote accumulation before it became dangerous. Modern masonry heaters, which are essentially sophisticated versions of Lars's concept, use similar approaches to prevent creosote while extracting maximum heat. The safety record of properly built and operated masonry heaters is excellent, confirming that high heat extraction and safety are compatible when design is thoughtful. The spread of Lars's design through the Bitterroot Valley was steady but not explosive. By 1885, approximately 30 cabins had baffled chimneys built by Lars or by others copying his design. Each one performed better than conventional chimneys. Fuel savings range from 30 to 60% depending on construction quality and operation. But adoption was limited by several factors. First, the design required skilled masonry work. Lars was a skilled builder. Not everyone was. Poorly built baffled chimneys could indeed create the problems people feared. Smoke backup, inadequate draft, creosote accumulation. The design was forgiving of some errors, but not all errors. Second, it required understanding. To operate the system safely and efficiently, you needed to understand how draft, combustion, and heat extraction work. You needed to adjust the damper appropriately. You needed to maintain proper fires. This was more complex than operating a conventional stove where you just fed wood and hoped for the best. Third, initial construction cost was higher. The double wall design with baffles required approximately twice as much brick and twice as much labor as a simple straight chimney. Not everyone could afford the upfront investment, even though the lifetime fuel savings would more than repay it. Fourth, the cultural bias against anything that looked wrong. Even after Lars proved his design worked, many people remained uncomfortable with a chimney that had visible obstructions. It just looked wrong, and appearance mattered to people. Lars himself continued living in his cabin until 1896. His chimney provided efficient heat for 18 winters. He maintained it carefully, cleaning it regularly and repointing mortar as needed. The thermal mass remained sound. The baffles stayed in position. The system worked, as designed year after year. In 1896, at age 54, Lars sold his trapline and moved to Missoula, where he worked as a building consultant and mason. He built several houses with advanced heating systems, though none exactly replicated his mountain cabin chimney. The era was changing. Coal-burning furnaces were becoming common in towns. Central heating was emerging. The custom-built, site-specific solutions that made sense for isolated trappers were being replaced by manufactured standardized systems. Lars's knowledge was valuable but increasingly obsolete. He died in 1912 at age 70. His original cabin in the Bitterroot Valley was used by various trappers and homesteaders until the 1930s. The chimney continued functioning throughout. When the cabin was finally abandoned, the chimney remained standing for another 2 decades, a brick monument to forgotten engineering. Eventually, weather and vandalism brought it down. Today, nothing remains of the physical structure, but the principles Lars demonstrated remain valid. Modern masonry heaters, also called Finnish heaters or Russian fireplaces, use the same heat extraction and thermal storage principles. These heaters have complex internal passages that force hot gases to give up heat to massive brick or stone structures before exiting. A properly designed masonry heater can extract 75 to 90% of the heat energy in wood, compared to 30 to 40% for conventional wood stoves. They can store heat for 12 to 24 hours, releasing it slowly and evenly. They're more efficient and more comfortable than conventional heating. They're also expensive and require skilled construction. The Masonry Heater Association exists to promote these systems and train builders. But masonry heaters remain niche products. Most homes use forced air furnaces or heat pumps. The custom-built thermal mass heating systems are for enthusiasts willing to invest in unconventional approaches. Lars was doing masonry heating in 1878, decades before the concept was formalized. He was applying Norwegian traditional knowledge to American frontier conditions. The broken chimney that everyone said would kill him was actually a sophisticated heat extraction system that modern engineers would recognize and respect. The practical lessons from Lars's work apply to modern heating challenges. First, waste heat recovery is enormously valuable. Most heating systems waste significant energy through hot exhaust. Capturing that waste heat multiplies system efficiency. Modern condensing furnaces do this, extracting so much heat that water vapor condenses, but even more could be done. Residential heating is still wasteful by the standards Lars achieved. Second, thermal mass stabilizes temperatures and reduces peak heating loads. Modern homes, built with lightweight materials, have almost no thermal mass. They heat and cool rapidly, requiring constant energy input. Adding thermal mass, whether through masonry heaters, concrete floors, or other methods, creates thermal inertia that reduces energy consumption and improves comfort. Third, draft control enables optimization. Conventional wood stoves with no air control burn inefficiently. Modern EPA stoves with adjustable air intakes burn much more efficiently by controlling combustion rate. Lars' damper achieved similar control. The principle is universal. Controlling airflow optimizes combustion. Fourth, integration of multiple principles creates breakthrough performance. Lars didn't just add baffles or just add thermal mass. He combined heat extraction, thermal storage, draft control, insulation, and careful operation. The integration created efficiency far beyond any single improvement. Modern high-performance buildings use the same approach, combining insulation, air sealing, passive solar, thermal mass, and efficient systems. It's the integration that delivers order of magnitude improvements. Fifth, what looks wrong might be right. Lars's chimney looked broken. Every conventional indicator said it was dangerous and wouldn't work, but appearances were deceiving. The design was sophisticated, intentional, and highly effective. We should be cautious about dismissing unconventional approaches based solely on appearance. Results matter more than conformity. The barriers to adopting baffled chimney designs today are primarily regulatory. Building codes specify minimum chimney dimensions, maximum restrictions, and various safety factors. These codes are based on conventional straight chimney designs. A baffled chimney, even if more efficient and equally safe, might not meet code because it deviates from standard assumptions. Insurance companies are reluctant to cover unconventional systems. Building inspectors don't know how to evaluate them. These barriers exist for good reasons, preventing dangerous experimentation by unqualified builders, but they also prevent beneficial innovations. We need pathways for testing and approving innovative designs without requiring decades-long adoption cycles. Modern masonry heaters face similar regulatory challenges and have gradually gained acceptance through testing, documentation, and advocacy. Lars's baffled chimney could follow a similar path if advocates pushed for it. The economic calculation for modern implementation is interesting. A custom masonry heater today costs $10,000 to $25,000 installed. For a home that would otherwise use $5,000 per year in heating costs, payback time is 2 to 5 years. For homes with lower heating costs, payback is longer. But over a 30-year building life, the savings are substantial. The challenge is that most people optimize for first cost, not lifetime cost. A $15,000 heating system seems expensive compared to a $3,000 furnace, even if the masonry heater saves $2,000 per year and the furnace costs $2,000 per year to operate. We're bad at valuing future savings against present costs. This is a general problem with efficiency improvements. The story of Lars Henriksen and his broken chimney trick reminds us that conventional wisdom is often wrong, that efficiency improvements can be dramatic when multiple principles are integrated, and that what everyone knows to be true might actually be false. His neighbors swore his chimney would kill him. It kept him alive and comfortable during a blizzard that nearly killed them. The difference was knowledge, understanding, and willingness to build differently. Today we face heating challenges that require innovative solutions. Climate change makes efficiency imperative. Fuel costs are rising. The old ways of building and heating are not sustainable. We need better approaches. Some of those approaches will look wrong to people trained on conventional systems. Some will violate current building codes. Some will seem dangerous or impractical. But results matter more than appearances. Lars's cabin at 8 degrees during a 39 below blizzard, maintained with a moderate fire and 1/3 the fuel his neighbors used, proved that unconventional approaches can outperform conventional ones by enormous margins. The question is whether we're willing to learn from that proof, whether we're willing to question our assumptions, whether we're willing to build chimneys with deliberate obstructions if the obstructions create efficiency improvements. The broken chimney that everyone said would fail was actually the most advanced heating technology in Montana territory. Sometimes broken is better than fixed. Sometimes wrong is right. Sometimes the person everyone mocks is the only one who truly understands. Lars Henriksen understood. His 47-degree temperature advantage proved it. We should pay attention to that proof and ask ourselves what other broken-looking innovations we're dismissing without investigation. Before we wrap up, I want to ask you one more time to subscribe to this channel if you haven't already. Hit that subscribe button, turn on notifications, and join our community of people learning from historical innovations. We uncover forgotten knowledge that could still change how we live. Your support makes this work possible. Thank you. The blizzard of January 1881 was a test that conventional heating systems failed, and Lars's broken chimney passed. That test should have changed how everyone built, but it didn't. Most people continued building conventional chimneys because they looked right, because they were familiar, because building codes, when they eventually arrived, specified conventional designs. The knowledge Lars demonstrated was absorbed by a small community of masons and enthusiasts who built masonry heaters and thermal mass systems. But the broader building industry moved toward standardized, mass-produced heating systems that prioritized convenience and first cost over efficiency and performance. We're now, more than a century later, rediscovering that maybe Lars was right. Maybe extracting heat from exhaust is worth the complexity. Maybe thermal mass improves comfort and efficiency. Maybe controlling draft optimizes combustion. These aren't new insights. They're very old insights that we forgot and are now remembering. How many other Lars Henriksens have there been? How many other broken-looking innovations that actually worked better? How much knowledge have we lost by dismissing unconventional approaches? These questions should haunt us as we face modern challenges that require innovative solutions. Thank you for watching this story about Lars Henriksen and his remarkable chimney design. If you found value here, if this changed how you think about heating or innovation, please share it with someone who might benefit. And remember that when everyone swears something won't work, they might all be wrong. The broken chimney might be the only one working properly. The fool might be the only wise man in the valley. Don't trust appearances. Trust principles, trust evidence, trust results. Lars trusted his knowledge over conventional wisdom, and it kept him 47 degrees warmer than everyone who trusted what everyone knew to be true. Sometimes what everyone knows is wrong. Have the courage to find out.